Okay, everybody, the weather has changed. It is a cold, windy, rainy day today, and that makes the barn that much colder. So try to stay warm here. So we've got one more section that we want to cover in our probability chapter or unit, and that's called calculated probabilities. Okay, so we're going to look at a couple more types of probability. The first one that we're going to look at is conditional probability. And conditional probability is a type of probability that occurs when we know something about the event. Okay, so this is probability used when we are given a condition of the event. Okay. And the most common place that we see conditional probability used in the kind of sense of what we've been talking about would be going back to gambling, okay? So most definitely gambling. So we've all heard or watched movies or seen it or whatever about counting cards, okay? And how the casinos consider counting cards illegal. I don't see it that way, okay? I see it as someone who's good at math, just working the angles. All right, but counting cards is where conditional probability comes into play. So the idea is if you're playing a game where you get to see what the cards are, like in blackjack, they put the cards face up. If you can keep in mind what cards have been played, then you have a better understanding of what cards are still in the deck, which means you're given a condition or you're calculating a condition about the deck. So as an example, let's say that a number of cards were dealt out of the deck and they happen to be all face cards. Okay, so let's say that there are eight cards that were dealt out and all 8 of them are face cards. Now the question becomes, when they deal that next card from the deck, is it more likely to be a face card or less likely? So if eight of the 12 face cards are out, then there's a higher probability that the next card that's dealt is going to be not a face card because there aren't as many left in the deck. And this is how people that do count cards, this is how they do it. They keep track of the large numbers and the small numbers. And as more and more large numbers come out of the deck, are dealt out of the deck, they can keep in mind that that means there's more small cards left in the deck. Okay, now I know it's just like, okay, wait a minute. It's a lot of keeping things in your mind. Now, for those of you that are old enough to gamble and have gambled, what you notice is when you go to a casino, they don't play with just one deck because just about all of us could learn to count cards when there's just one deck. Again, 12 face cards. If 8 of them are out, it means there's only 4 left in the deck, so you're gonna be lucky to get one. Okay. So in casinos nowadays, they use a shoe. I don't know why they named it a shoe, but whatever. And in that shoe holds not just one deck, but anywhere between 4 and 6 decks. So instead of shuffling up one deck, they shuffle up 6 decks all together. Okay, 6 decks all together. Now, if there are 12 face cards in one deck, that means there's 72 face cards in 6. So as those cards are being dealt out, is it going to be a lot harder for the people playing to keep in mind all 72 face cards? Okay, so that's kind of the gambling way to kind of get rid of the counting cards thing. But some people can still do it, okay? But anyway, so that's the use of this in kind of everyday life. But the way that we're going to see it is, in math problems. Okay, so we're not going to be playing blackjack or anything like that. We're just going to do basic math problems here. So the notation for conditional probability looks like this: the probability of A given B. Now that's not a division line; it's a straight up and down line. And in math, that's the symbol for given. So this is said the probability of A given B. Okay, that's how you say that. So what's going to happen is the condition is going to come second. We're going to find the probability of A, but there's a condition to it. Okay, so let's look at an example where we're just going to draw a single card from the deck. So draw a card. Okay, just one card. And I want us to find the probability that it is a queen given that it's a face card. Okay. So this is the given. This is still what we're trying to find. We want the probability of queen, but we know that it's a face card coming to us. So whatever, we've been counting cards, or maybe the card kind of floated up and you saw that it had a face on it. You couldn't quite tell which face it was, but for some reason we know that a face card is coming to us. Okay, which means that eliminates all 52 cards. We're not interested in all 52 because we know it's a face card. So that given is going to give us the bottom of our fraction when we go to do this. So instead of dealing with 52 in the denominator, we're going to deal with how many face cards there are, which is 12. So it changes the denominator of the fraction. Now, of those 12 face cards, how many are queens? Okay, 4 of them, right? So 4 of the 12, which would give us 0.333, okay? Or 33.3%. So if you know it's a face card, you've got a 1/3 chance of getting a queen, okay? Now, let's just say that I asked you to find the probability of getting a queen. Okay, so still drawing a single card, new deck, fresh problem. Now, no given on this one, okay? No given, and since there's no given, that means that we're interested in the whole deck, which means our denominator is 52. Okay. How many queens are in the whole deck? 4. Okay. So here the probability is 4 out of 52. 4 divided by 52. And that gives us our 0.077. So 7.7%. So do you see what happens when you're given a condition? Do you see how it changes the probability? Okay. Now, I'm going to turn this around and ask you this question just with the same information but in a different way. This time, I want you to find the probability of getting a face given that it's a queen. Okay, so the order definitely matters. In this case, what you know that's coming to you, you have a condition that it's going to be a queen. I don't know how you know that, you're psychic, whatever, but you know a queen is coming. So remember that this is going to give you the bottom of your fraction. So how many queens are there in the deck? There are 4. Now, if we're just looking at those 4 queens, what's the probability that if you pull one of those 4 queens, it's going to be a face card? Aren't they all face cards, right? Because they're all queens, yes? So this would end up being 4 out of 4, or 1, or 100%. So if you know that it's a queen coming to you, then for sure you're going to get a face card. Okay, and if that's what you're looking for, woohoo! Okay, so notice how the givens, the condition, definitely changes things. Okay, it definitely changes things. Let's just look at a couple more here. Let's say that we want to find the probability, so still our draw card, we want the probability of getting a heart given it's a black card. So again, I don't know how and necessarily you know these givens, okay? Again, did you cheat or however. But for some reason, you know that the next card coming out of the deck is a black card, okay? So you want a heart though. So right off the bat, is this looking good? It's not looking too good, is it? So the way that we look at this is we start with the given, and that's gonna give us the denominator. So of the deck, half is black, which is 26. So we have 26 black cards on the bottom. Now of those 26 cards, how many are hearts? right? 0 of them are hearts. So in the end, if you want a heart, but you know it's a black card that's coming, things aren't looking too good for you, okay? So it's definitely possible with these givens to get 0% or 1 or 100%, okay? It's definitely a possibility. Okay, so again, it's given where you're given a condition. So you've got a couple card problems that you'll have to deal with, but nothing really beyond what we've done right here. And again, people go, when the heck would I ever use this? Well, again, this is in gambling. You'd use it in the idea of counting cards, but we also use this in an everyday scheme. When you're looking at any given problem, okay, or any problem, I shouldn't say the word given. When you're looking at a problem, there are always little things that you know. Remember subjective probability, the probability of personal knowledge? So there are always these little outside things that you have information about, so that when you make a probability, there is some given on there. Now, do you calculate it? No, but this is what it would look like if it was actually calculated. Okay, so I know given is not everybody's favorite thing. So, something that goes along with conditional probability is the idea of independence. Okay, independence. And this says if, let's not write it that way. Sorry, let's write it in a different way. 2 events are independent if the occurrence of the first event does not affect the occurrence of the second event. Okay, so independence becomes an important thing when it gets to probability, and again, the reason why is because these things, conditions or independence, they will change your probabilities. So conditional means that we're definitely not independent. There's something weighing on us, okay, something we know. Now, independence means that 2 events are not going to affect each other. So the idea here is that if you flip a coin, okay, it lands, whatever, and you pick it up and you flip it again, is the second flip at all affected by the first flip? Okay, and it's not, is it? Which is why we use a coin, because it's 50-50, and each time you flip it, you have a 50-50 chance of getting heads or tails. So flipping coins would definitely be independent. Rolling dice, okay? You got a pair of dice in your hand, you roll the dice, you get, adds up to a 7, you pick up the dice, you roll it again. Are you more likely to get a 7 or less likely to get a 7? It doesn't matter, does it? Because each time you roll the dice, you shake them and you roll, and they are independent of each other. So rolling dice would be independent. Now, when we think not about drawing a card from a deck, but dealing cards out of the deck. So if you start with a full deck in your hand and you start to deal cards out, okay? So the first card gets dealt out. Now when you turn to the second person to deal out the second card, has the deck changed? It has, hasn't it? Because there's a card over there. So the probabilities for this second person, they alter just a little bit. Conditions, right? So you deal out the second card, then you turn to the third person. Now for the third person, has the deck changed again? Okay, there are 2 cards out. which means there's only 50 cards left in the deck. So all of the probabilities are kind of altering each time you deal. So as an example here, let's say that you really want the ace of spades. It's your favorite card, you definitely want it. So, but you're third in line, okay, to be dealt to. So the first person gets a card and it's face up and whew, it's a 7. Okay, and the second person gets a card and darn it if they don't get the ace of spades. Okay, so now when it comes to you, if this deck was a full deck, you'd have a chance of getting the ace of spades, right? But now that the ace of spades has already been dealt out, has the deck been changed and has your probability been affected by that? It most definitely has, okay? So we say dealing cards is not independent. Dealing cards is not independent. All right, so independence, if there's no effect from one step to the next, one event to the next, then we've got independence. If there is an effect, if the probabilities are affected even at all, then they are not independent, or I guess we could say dependent, okay? All right, so what that leads us to is the multiplication rule. Which says if A and B are independent, then the probability of A and then B is equal to the probability of A times the probability of B. So the idea up here is that it's going to be the probability of A and B, but I include the then because what needs to happen is you need to do one event and then another, one after another after another. And if they are independent, this just becomes a nice multiplication problem. Okay, so we said flipping coins was independent, so let's go and flip a coin. I want the probability of getting a tails and then a heads. Okay, so first thing I want is a tails, then I want to pick it up, flip it again, and I want it to be a heads. Now again, that coin is fair and it's independent, which means that we can simply go the probability of tails times the probability of heads. Okay, now it's a coin, so this is a little bit on the boring side, but basically there is a 1/2 probability of getting the tails, and then multiply a 1/2 probability of getting the heads, right? Okay. So if we multiply this together, we get 1/4 or 0.25. So the thing to notice here is that when you want things to happen in order, in succession like this, the probability should go down. It should get harder, okay? And that's the case. You don't just want a tails, you want a tails followed by a heads, which means that it's going to be a little bit harder to get that to happen. So instead of a 50%, you're down to a 25% chance. Okay, so multiplication means we're definitely going to see probabilities get smaller. Okay. All right, so let's see. Let's look at another example here. Draw 3 balls from a bag, and I want the probability of getting, oh wait a minute, I forgot something. Sorry about that. So you're going to draw 3 balls from a bag. Let's just start the whole problem over. Okay. Draw a ball from a bag 3 times with replacements. find the probability of getting a red, a blue, and a red. Okay, and let's see, here is our bag. Okay, so where's my blue pen? Somewhere over here. We'll start with the red. Okay, so let's say there's some green balls in here. And I have a bright blue, so we just have to use this blue. Okay, so there is our bag. Okay, and we're gonna draw some balls out of this bag. Okay, so for those of you that maybe this isn't clear, I've got 4 red balls in the bag, 3 green ones, and 5 blue ones. Okay, so with that, how many balls do we have total? Because that's going to be important to us. So total, we've got 5, 4, and 3, which will give us 12. So there are 12 balls. Now, what I want us to do is to find the probability of getting red, blue, and then red again. But this said with replacement. So with replacement means that you're going to pull the ball out, you're going to look at it, you're going to go, ooh, it's red, and then you're going to put it back into the bag. So between each event, does the bag change? Or does it still have all the original balls in it? You've only pulled one out and you've put it back in. So there will always be 12 balls in the bag every time that you go to draw because you're putting your ball back in. So because of that, it means that things are independent. The probability should not change. There's always the 12 balls. So if we want the probability of red, blue, and then red, then we can find the probability of red times the probability of blue times the probability of red. All right, so we said there are 4 red balls. So the probability of pulling out a red would be 4 out of 12. Okay, you put that ball back in. Now we want to pull out a blue ball. There are 5 blue balls, and we still have 12 balls in total. Put the ball back in. Now we're going to go for another red. We want another red to come out. So there are still 4 red balls in there out of the total of 12. So we're going to multiply these 3 probabilities together. Now remember what I said. This is probably going to be a small decimal. So 4 divided by 12 times 5 divided by 12. Yep. So I got that this equals 0.046. Okay. So there's a small chance, 4.6%, that you're going to go red, blue, red. Okay. All right. Now, though, I want to change the problem a little bit. So we better make a little note here that this was independent. So what if I say this time, don't replace the ball. Okay, this time don't replace the ball. Now, again, I want you to find the probability of getting a red, a blue, and then a red. But the problem is here, if you don't replace the ball, if you reach your hand in, you grab the ball, and I don't know, you throw it, I don't know, the bag is not the same after each pull from the bag, is it? There are fewer balls in there. So are our probabilities going to be affected a little bit? And they are, which means that this is not independent. Okay, so this one is not independent. Now, that doesn't mean that we can't can't do the problem. It just means that we have to think about it a lot more. Okay? Not a lot, a little more. So we want the probability of red, then blue, then red. Okay, so fresh bag with 12 balls in it. There are 4 reds, so we start by going 4 out of 52. 52. Hello, not the deck of cards. 4 out of 12. Now, we're holding a red ball in our hand. We reach in to grab another ball, and we want it to be a blue. Now, there are 5 blues in there, but because you already have a red one in your hand, how many balls are there? Okay, there are only 11 balls left in the bag. Do we agree? Okay, now you have a blue and a red ball in your hand. You're holding on to them. You go back to the bag one more time, and we want another red. But are all 4 of these red balls still in the deck? Or, I don't know what's wrong with me, not the deck, the bag, okay? One of them is in your hand. So how many red balls are left? There would be 3. And because you have 2 balls in your hand, how many balls are left in the bag? Only 10, do we agree? So what we're seeing is conditions. The deck, or the ball, the bag changes after every event. So this is a conditional probability. Now again, it didn't mean we couldn't do it. We just have to think about that idea of conditional. So here we go 4 divided by 12 times 5 divided by 11 times 3, times 3 divided by 10. Now, it doesn't change it a lot, but it does change it a little bit to get 0.045. And if there were more balls in here, it would change it quite a bit, okay? But our little example. So also though, this becomes important as to why we round out to a couple decimal places. So I know it might not seem like a lot, but which one of these is more likely to happen, okay? It's more likely that when you use replacement, you're gonna get a red, blue, red than without replacing the balls. Okay? So we see a difference there. Okay, one more here. So we talked about dealing cards from the deck, and apparently I'm stuck on that since I keep saying deal cards, deal balls, whatever it is we're doing. So we are going to deal 5 cards from the deck. And I want the probability of getting all red. Now, the thing with this problem is that most people see all red and they just think, oh, just all red and then divide by 52, okay? But the idea here is as you deal 5 cards, how many things are actually happening? Aren't we doing 5 things? Deal, 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 deal. So what this actually is the probability of red, 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 red. So it's actually 5 things happening there. Now the problem is what we said about being when we deal out cards is the deck has changed a little bit in between each deal, right? Which means that if we want to do this, we have some conditions on this. Now again, we can still do it, we just have to think about it a little bit. So when you go to the deck, fresh deck, okay, and you want to deal out that first red card, there are 26 out of 52, right? Okay. So I just dealt a red card over there. Now we want to deal out another red card. But now if there's a red card over there, how many red cards are left in the deck? There are 25 out of how many cards in total? 51. Okay. All right, deal out another red card. Now we want a third. The numbers are going to drop again. Now there are only 24 red cards out of 50. Okay, and you see the process, we're going to do this 2 more times. So there'll be 23 out of 49. and then there will be 22 out of 48. All right, now, what we're gonna notice is that this probability, because there are 5 fractions multiplied together, is gonna get pretty small. So take a second, 26 minus 52 times. And it's always easiest to just plug this whole thing into your calculator. Just be careful as you plug it in. But don't try and do this piece at a time. That's just a pain in the butt. So I got 0.025. Okay. So even though half the deck is red, if you want to deal out 5 red cards in a row, there's actually only a 2.5% chance that that's going to happen. Okay, so it's not all that likely, is it? But do you see how most people wouldn't think that? They'd say, oh, well, half the deck is red, so sure, at half the time you're going to get 5 red cards. So the probability is definitely affected by each dealing, and as we do more, as we want one red card after another, it gets harder and harder and harder, or rarer, that that's going to happen. It's very rare that somewhere in there wasn't a black card. Okay. All right, now let me just look a little bit more here. Make sure I got everything. Let's see what's on page 677. Okay, we did that. Yeah, okie dokie, looks good. All right, so these calculated probabilities, again, we've got independent and not independent, and we've got that multiplication, but we also have that conditional in there. All right, so I know that's a lot to keep straight, so it requires practice. Probability definitely requires practice because there's almost always some rule that you have to think about, okay? So I always tell people that when you're doing probability, before you put your answer down, you say, was there something that I needed to think about? Okay, did I need to worry about independence? Did I need to worry about replacing balls back in the bag? Was there something I'm missing? Because a lot of times there was. Okay, so anyway, have some fun with that, and I will see you next time.